In his collection of autobiographical stories, Richard Feyman talks about throwing a plate up in the air and watching how its motion developed. He figured out the motion of the rotating plate, and he writes in his book that I discovered that when the angle is very slight, the plate rotates twice as fast as the wobble rate, 2 to 1. It came out of a complicated equation. For my project, I investigated rotations, made a VPython simulation, and did a real-life demonstration. To start thinking about rotations, we can set up a space frame, which is the standard XYZ coordinate system. Then we can set up a body frame, the E1, E2, and E3 coordinate system, which can rotate with the object of interest. Rigid body rotations are governed by Euler's equations. Shown here are Euler's equations for a system with zero torque. I1, I2, and I3 are the moments of inertia about the E1, E2, and E3 axes, and omega 1, omega 2, and omega 3 are the angular velocities about the E1, E2, and E3 axes. In my setup, I orient the plate in the E1, E2 plane, so I3 is the moment of inertia about the plate's center, and omega 3 describes angular velocity about the plate's center. In this case, I3 is equal to 1/2 mr squared, and I1 and I2 are both equal and equal to 1/4 mr squared, where m is the mass of the plate and r is its radius. Since I1 equals I2, Euler's equations can be simplified to this form. Defining a new quantity, omega, Euler's equations can now be rewritten in this form. An interesting thing to note is that one can take the derivative of omega 1 dot, yielding the above expression. Using the fact that omega 2 dot is equal to negative big omega, omega 1, you could make a substitution for omega 2 dot in the first equation and arrive at the third equation, which should look like simple harmonic motion. The acceleration is equal to negative kx. I made a VPython program to simulate the motion of the wobbling plate. From Euler's equations, since the derivative of the angular velocity about the E3 axis is equal to 0, we know that omega 3 is constant. In my simulation, I gave the plate an angular velocity about the E3 axis as well as the E1 axis. The angular momentum, shown by the yellow arrow in this figure, is calculated by taking the vector of the moments of inertia times the vector of the angular velocity. In the space frame, since angular momentum is conserved, the angular momentum arrow stays in the same place throughout the simulation. However, omega and the E3 axis rotate around the angular momentum vector. In the body frame, E3 would stay fixed, and L and omega would precess around the E3 axis. In my simulation, I used Euler's equations to rotate the axes of the plate about the omega vector in the space frame. I then investigated the ratio of wobbles to rotations. First, look at the red arrow. It makes one full rotation during the duration of this clip. Next, look at the location of the plate on the x-axis. It goes down, and then up 1, down, and then up 2 wobbles. The ratio of wobbles to rotations is in fact 2 to 1, not 1 to 2, like Feyman thought. As shown by this simulation, we can clearly see that the plate wobbles twice for every one time that it rotates in the space frame. I tested out the spin to wobble ratio with a demonstration. First, watch the rotations of the plate. It starts there, 1 rotation, and about 1.5 rotations. Next, count the wobbles. 1, 2, 3. A wobble to spin ratio of 2 to 1. Here's another view of the plate. We have 1 wobble, half a spin, and 2 wobbles with a full spin.